I hear the boss.
So yesterday we had gone through for, I don't know, 20, 25 minutes. We derived the ideal gas law in what we call a theoretical derivation using all this physics. We came up with the same thing that was developed experimentally, but taking that derivation from both angles, I do think gives us an idea of how reliable that ideal gas law is. Now, I do want to mention, tomorrow we have our next reading quiz. Tomorrow's reading quiz is not the nicest reading quiz you will ever take on. My recommendation is to read it several times, taking breaks in between times that you read it. Read it 4 or 5 times, but don't read it consecutively. Read it through, get away from it for a while, then come back later on and read it again. Yes? It's not very many pages. 4, Does anybody know how many pages it is?
4.
Only 4?
4.
Okay. Now, what the reading assignment is, it tells us what we do if you don't have a gas that's behaving ideally. We have PV equals nRT. Well, that's when a gas is behaving itself, where the particles don't get in one another's way, where the particles are not sticking to one another. What if they do, though? So that's what our reading assignment is going to be about. Like I say, it's dense. It's dense. I will take some of the burden off of you by telling you that you will not have to calculate anything on the reading quiz tomorrow. It's going to talk about this equation and what do we do with this equation when a gas is not behaving ideally. But you won't have to use the equation. You just have to understand how things are affected.
Do I have to tell you the equation?
Nope.
So could a question be like?
Let's see. I think I asked it. I mean, there wind up being correction factors in this equation. I may ask you generally about the correction factors, but you won't have to do anything mathematically, even like recite what the actual equation is. Yes? Okay. James, you snuck in. Here's your reading quiz from yesterday. We do that quiz too. Check for this. Okay, so one of you came in this hour and said, "Oh man, if you do any more deriving of stuff, I'm going to have PTSD." I found that to be funny. We are going to derive more though today. However, as I told you at the beginning of yesterday's derivation, this is by far, it's not even close, this is by far the longest and most obnoxious derivation we're going to have. You'll see today, when I have to derive something, it's just going to be like one slide. Everything happens in one slide and then we're done. So it is not like, you won't have anything like what we just did yesterday. So if we can move on, in fact, before we move on to the next slide, I want to take you back for a second to the last thing that we had on the second to last slide. It says that PV over N is equal to 2 times the kinetic energy of the gas over 3. Now this is the point at which I said, oh hey, remember how kinetic molecular theory says that the kinetic energy is proportional to the temperature? And so that's where we were able to put in temperature to this, and we have this relationship that includes all 4 of the gas variables. And so we renamed the K as R, and the R value is constant for every gas, as long as it's behaving ideally. That allowed us, or that relationship between kinetic energy and the temperature allowed us to do that. Now, on the next slide, there's not really a derivation that's happening here, but I will say this. We saw that PV over N is equal to RT. That is the ideal gas law. But we also saw on the previous slide, PV over N is equal to 2/3 times the kinetic energy. And so this relationship right here allows us to have an actual expression of the kinetic energy. So rather than just saying, well, kinetic energy is proportional to temperature, we have this relationship that tells us the actual proportion. Kinetic energy is 3/2 times R, that's a constant value, times the temperature. So this gives us the actual relationship between the kinetic energy and the temperature. Now, not very often will you ever have to use this formula, but I do want you to know that there is a mathematical connection between what the kinetic energy of a gas is and what its formula, or what its temperature is. Now, one of the things that I mentioned, you can see it down here. Whenever you use an energy term with the ideal gas constant R, anytime R is in a formula that involves energy, you have to use this value of R. You don't just choose any old value. And the reason for that is because if you notice the unit on this thing, we learned R, one of the values of R is 8.31 kilopascals times liters over moles Kelvin. I've got it up on the board over there, one of our 3 values of R. If your pressure unit's in kilopascals, then you use this value of R. But then something changed about this. And the reason is because a kilopascal times liter is the same thing as a joule. The joule is the metric unit for energy. And so I don't suppose you've ever seen this before, but it turns out that, yeah, the term joule is the exact same thing as kilopascal liter. So those are interchangeable. And so when I find the kinetic energy, the answer is going to be in joules per mole. If I just put in whatever the temperature is here, I'll get how many joules per mole there are. And that's because the joule term is in R. The per mole is in R. But the temperature, this Kelvin in the denominator of the R unit, cancels out the Kelvin in the temperature term, so that I'm just left with joules per mole. This formula then tells us, because gas particles are in a constant state of motion, the kinetic energy of those gas particles would be calculated like this, and the unit would be joules per mole of that gas. It's not joules for every single particle, it's joules per 1 mole. Now, on the next slide, I'm kind of, okay. On the next slide, I was going to mention what I have in the back of the room, but I'll have to do that later in the hour. In fact, no, I'm going to do this right now. I have to get this thing ready. So I'm going to turn this around so that you can see to the back of the room. You may have to zoom that in if you're watching it online. Hey, oh my goodness. Always a crowd pleaser. Back here, I have a device. We have a green liquid in here. The green liquid is nothing more than water with green food coloring. I colored it green so that you could see it in here and you wouldn't have to sort of try to focus and see where it is. Now, what I have is it's a flask. I'm shaking it because I want to see. I can't tell unless I shake it. There is some liquid in the bottom of this flask. I'm going to add a little bit more. It's ethanol. Care to smell the ethanol? It's so good. Love it. Anyway, I'm going to take just a little bit, a couple milliliters of ethanol, and I'm going to squeeze it in. There's already ethanol in there. You can see it go down to the bottom. And then I'm going to take the dropper and actually force it in so that the right side, I do this every hour because I'm facing you, I keep wanting to call it the left side, but looking from your perspective, on the right side, this side, there is air, but now some of the ethanol is vaporizing, and something is happening, I believe, in that U-shaped part. This side, the left side, is open to the atmosphere. The right side is not open to the atmosphere anymore. It has air trapped in there, and ethanol vapor is being produced. What do we see happen? You see anything happening? It's not very fast. Yeah, the right side is going down. It's getting pushed down, and the left side is getting pushed up. Do we have a name for this device? Yes. Careful. It's a manometer. Manometer. It's different from a barometer. A barometer is just a single straight tube, that has mercury in it. You could use water for a barometer too, but because water is so much lighter than mercury, you'd have to use about a 30-foot tube for water to do the same thing as a mercury barometer. Mercury is 13 times more dense than water, so it takes a lot more force to push mercury around than it does to push water around. Is it still working? Yeah, very slow. That's why I wanted to do this now. We'll look at it at the end of the hour. As the ethanol vaporizes, it's increasing the pressure on the right side. The left side has a constant pressure, it's the pressure of the air. But there's air on the right side, plus now ethanol vapor that's coming out. And so once the movement stops changing, we'll have, like the right side is going to be up here and the left side is going to be down here. There'll be a clear difference in the levels. Once that happens, the difference in the levels is going to tell us what the vapor pressure of ethanol is. It'll stop moving, which means it comes to equilibrium. So we'll know the equilibrium vapor pressure. Now, when I read that difference in the levels, that's not actually the unit torr. Remember what torr is the same as? Millimeters of Hg, mercury. Remember, like I just said, mercury is a much more dense liquid, and it takes a lot more force to push mercury around. So I would take the difference in the levels of water and divide it by 13. That would be the actual vapor pressure and torr of the ethanol. Where did the 13 come from? It's because ethanol is mercury is 13 times more dense than liquid water. So yeah, you need 13 times more force to push mercury around than you do for water. Okay, so we'll turn around and look at that at the end of the hour. Man, yesterday when I tried this, it immediately gave me that change in the elevation so quickly. I think I have a leak someplace on this, and I don't know where. So anyway, I'm going to just leave that and let the ethanol vaporize and hope for the best. It was very clearly two different levels last hour, and then I didn't know if somebody had bumped it or whatever. That's why I changed it. As you can see, there's two different levels there. So let's see if it keeps. Sorry. Okay, now I would like to ask you. Oh, I left that stylus in the back.
Come on, hoodie.
This is going to be another derivation of a formula. Now I could, for any of these formulas, I could. Ready for this? This is way better than DBQs and dumb stuff like 8 push.
Yes,
I mean, who cares about that?
Like, who cares?
Right?
Thank you.
Round of
Thank you,
applause for
sir.
that.
Sorry.
Who's bro?
Yeah, I know. I don't know who that is.
Okay, so anyway, what we're going to look at in this relationship is, can we calculate how fast gas particles move? Like, if I take a very fragrant chemical like acetone, it's got a much more pronounced fragrance than ethanol does. Ethanol smells great, but it doesn't have an overwhelming smell. Acetone does. If I take the lid off of an acetone bottle here, after several seconds, I'm going to say, oh yeah, I smell the ethanol. And then pretty soon, Udayan and Rishi, oh yeah, I can smell it. And then, eventually, it may or may not go all the way to the back of the room, depending on what the air in the room is doing. If the air is all moving that way, then maybe you won't smell it in the back of the room. But how fast should those particles get from the container up in the front of the room out to you? Do gas particles, do they fly around so fast that they're moving at the speed of light? Are they moving at the speed of sound? How fast? Well, this is a way that we can calculate. I'm not going to just give you, I want you to see how we get these things. When I say things, how we get these relationships. So we know some things about kinetic energy. We know, we just saw on the previous slide, kinetic energy is calculated by taking 3/2 times R times the temperature. There's kinetic energy. But also we know of kinetic energy, the very definition of kinetic energy is 1/2 mv squared. And anybody that's been through physics, you could, you dream at night about 1/2 mv squared. You see it so much. Now I do have another term in front of my 1/2 mv squared. Remember how the unit over here was going to be joules per mole. I would like this side to be joules per mole too. This capital N subscript A represents Avogadro's number. 6.02 times 10 to the 23rd power. What's that doing there? Well, it's because the 1/2 mv squared applies to what? Is that to the whole sample of the gas? No, it's just to one particle. One thing has its kinetic energy calculated by 1/2 mv squared. One single particle. So if you take that one particle and scale it up by Avogadro's number, you'll have the kinetic energy per mole. So this calculation gives the kinetic energy per mole, and this calculation gives the kinetic energy per mole. What we're going to do is we're going to put that term and set that equal to that term. And let's see what it looks like. So one calculation of kinetic energy is Avogadro's number times 1/2 mv squared. And that's equal to the other expression of kinetic energy, 3/2 RT. Now the question is, how fast do gas particles move? What I'm going to do then is I'm going to solve for that V term. Now this V, keep in mind, is a lowercase v. What does it stand for? Velocity, not volume. The next slide is going to have a V, that's volume. So capital V is volume, lowercase v is velocity. Make sure you keep those straight. So I'm going to solve this one for the velocity, which means I have to get the velocity by itself. This is just a very simple algebra exercise that all of us could do, but I'd like to go through it with you. If I take, and again, I'm trying to get that velocity by itself, I'm going to multiply both sides by 2. Because I've got a 2 in the denominator there and a 2 in the denominator there. The first thing, very simple, get rid of the 2's. Multiply both sides by 2, gets rid of those. Then I'm going to get the V by itself by dividing out Avogadro's number and dividing out the mass. So it looks like this. V squared equals 3RT, that's what's on the right, 3RT, the 2 is gone, divided by NA, which is Avogadro's number, times the mass. Okay, now, is there a way to clean this up more? Yes, there is. Look at the denominator with me. What was M? The mass. Mass of what? A gas particle. That's the mass. Look up here. 1/2 mv squared is referring to one gas particle, right? So the M that I'm bringing down is the mass of one gas particle. Okay, what do you get? I don't want a number, I want a term. What do you get when you multiply the mass of one gas particle by Avogadro's number? Somebody just said it. The molar mass. That would be the mass of 1 mole of them. Yes? The mass of one particle times Avogadro's number gives us the mass of a mole of particles. That's the molar mass. So I'm going to rename this denominator. V squared is 3RT over the molar mass. And therefore, I know I've got that square root term, I'm sorry, that squared term on there, so I'm going to take the square root of both sides. And so this side, the square root of V squared is just going to be V. Now this has a special name because this is not a pure number, but rather it's an average number. Keep in mind, this is an average. You've got a mole of gas particles. You can't guarantee that all 6.02 times 10 to the 23rd of those particles are all moving the same speed. They're definitely not. Some are moving fast and some are moving slow. Maybe none of them are actually moving what the average velocity is. Maybe half of them are faster, half of them are slow. We don't know, but it's an average. So we actually have a name for this velocity. It's kind of a weird name. We call it the root mean square velocity. That's a mathematical term, and it has to do with when you're calculating, when you're taking the square root of a squared term. That's an average. We call it the root mean square. And that's equal to 3RT over the molar mass, the square root of 3RT over the molar mass. And I'll just write this in so you have it. I meant for that to have a space. It's not one word, it's 2 words. Root, mean, and then square. I've always found this to be a really dumb term. I would just as soon call it the velocity of particles, like the average velocity, and be done with it. But science purists call it the root mean squared velocity. And when you're doing the exercises in the book, you're going to get to a section that asks about things like this, and it's going to say, hey, calculate the root mean squared velocity of whatever gas at a certain temperature. And so if you know what the gas is, then you can find its molar mass. If you know what the temperature is, you got that, and you can find that. Just put the numbers into it. It's pretty easy.
So we get this equation as well.
I have a stack of the formula sheets, and you can take a look at this at any time. It does give you the kinetic energy of molecules is 1/2 mv squared. It does not give you that root mean squared velocity formula. So you'd have to either memorize it or be able to derive it. Okay, now just two other things about this root mean squared velocity. One of the things that is not one of the two is the fact that, remember, use only Kelvin for the temperature. The R unit, remember, is joules per mole Kelvin. So the Kelvin in R has to cancel with the Kelvin in the temperature. It's always the absolute temperature in Kelvin when we calculate with T. Two other things, though, R, you need to use 8.31 joules per mole Kelvin. I know that there's no energy expression in here, but it was derived out of an energy expression, so you have to use the R value that has to do with kinetic energy. The other thing, and this is going to be very strange, you're going to feel weird doing this. The molar mass that you find in the denominator, or when you put it in the denominator, must be kilograms per mole, not grams per mole. This is the only time in your whole life, I guarantee, that you'll have to use kilograms instead of grams with your molar masses. I know of no other time that you ever need to use kilograms except for in this formula. And why is that? Why do I have to use kilograms? Is that just to take an easy equation and make it difficult? No. Here's why. Because when we look at the units in this, the square root of 3RT over the molar mass. What are the units? Well, 3 doesn't have a unit. It's just a constant number. R is joules per mole Kelvin. And the T is Kelvin. And I'm telling you to use molar mass as kilograms per mole. Okay, now take a look what happens. The mole in the numerator is actually in the denominator of the numerator. This mole is in the denominator of the denominator. Do they cancel out? Yes. If you have a number or unit in the denominator of the denominator, it belongs up in the numerator. So I've got a mole in the numerator and one in the denominator, so the moles cancel out. The Kelvin, I've got a Kelvin in the numerator and one in the denominator of the numerator. They cancel out. Now all I'm left with is the square root of joules over kilograms. Well, the joule in physics is the metric unit of energy, which is also the metric unit of work. Work is force times distance. So the joule is actually a derived unit. It is kilograms meters squared per second squared. That's what a joule is in the numerator. That's just the joule. And then that's being divided by the denominator kilograms. Now, this is so easy.
What is this?
It's a joule.
This is not
a joule is a
chemistry.
kilogram meter squared per second
How
squared.
do we go from finding stoichiometry and now we're doing some random nonsense RMS?
It's not random at all.
Explain that to me.
Okay, I am about to explain it. It's going to make it nice. You ready? You got to listen though.
Locked in.
The kilogram that was in the joules is going to cancel with the kilogram that we use for the molar mass. And so in the square root sign, I'm just left with meters squared over second squared. So what's the square root of meters squared over second squared? Just meters per second. And so that's the unit of velocity. This is going to give us a velocity that's in meters per second. So that's why the molar mass in this case has to be in kilograms, so it'll cancel the kilograms that was in the joules. Now, do you need to know how these units work out? No, you're not going to have to manipulate those units. But I think it's good for you to see how that came about. And it really does help, of course. I asked you yesterday who's been in physics already, who's taken the full year. You have, right, Ferris? Did you take the full year of physics already? Yeah. Do you remember joules and how joules derived unit, kilogram, meter squared per second squared? Oh my gosh. Ferris, help me out. Come on. Anybody else been through a year of physics? Nope. Have you?
Just summer school.
Summer school, you don't learn anything in summer school. Everybody knows that.
Add my verb sheet.
Mr. Moore, is
Yeah.
it possible to summer school AP chemistry?
Yeah, you can actually.
Yeah.
You can.
Yeah.
Really?
You can just sign up for the AP exam without taking the
And
class.
then you'll pop up one.
Yeah, and then you get a 1 and you think, well, that was a waste of $100.
I have to memorize it.
Okay, so anyway, this let's see, just looking for a color to use. This is our formula for finding how fast particles move. You're going to find a very normal expected velocity of particles. It's not like in the hundreds of thousands of meters per second. It's not going like even as fast as the space shuttle goes. Space shuttle travels faster than gas particles at normal temperatures. So anyway, that's our root mean squared velocity formula. One quick other thing about this. How fast particles are moving. What variables determine how fast particles are moving? Looks like there's 2 variables. Temperature affects the speed of molecules and the molar mass. The 3 and the r are constants. They don't affect what the value of velocity is. So if we see that the temperature is in the numerator, if the temperature goes up, particles move faster. That causes the velocity to go up. If the molar mass goes up, it's in the denominator. So if you have a higher molar mass of a gas, you're making the denominator bigger, which makes the velocity smaller. You see that? So what gas would have the highest velocity of particles? What gas do you think? It has to be hydrogen. Yeah, the lightest gas, the lowest molar mass, has to have the highest velocity. Yeah. So the heavier a gas is, the slower its particles move. And that's assuming that the temperature is constant, right? If you change the temperature and the molar mass, well, you got to weigh both those out. Okay, so that's nice. We have now some tools in our toolbox for solving different kinds of problems. You could use the previous slide. If you were asked anything about kinetic energy of particles, you could use that. If you're asked about how fast particles are moving, you can use that. But wait, there's more. Like a good infomercial, right? That's not all you get. And if you stick around, we can take this ideal gas law, PV equals nRT, and we can express it in different ways. The ideal gas law is PV equals nRT, but it doesn't have to be PV equals nRT. If we have the mass of a gas given to us, what do? Well, we can convert to moles and then put it into that, or we can just come up with a new expression of the ideal gas law that includes mass.
It's pretty easy.
So, yeah, it really is not bad. Because if I have this calculation for molar mass is found by taking the mass over the moles of any substance. So if I solve this thing for moles, oops, I don't want to use that color.
It's mass over molar mass.
Moles, yeah, would be mass over molar mass. So if I have an expression for moles, I can replace the n in the ideal gas law with this. So that PV equals mass over molar mass times RT. And this is just as much the ideal gas law as what's on the top of the slide. PV equals nRT is our simplest form of the ideal gas law, but this is just as much the ideal gas law. You would use this if you have a problem in which you're given the mass of a gas and you need to find its molar mass. Just use this. So if you have an unknown molar mass, use that. normally I will get the molar mass out of the denominator, multiply both sides by molar mass, and you get PV times molar mass equals mass times RT. That normally is the way that we express it with mass in it. So this is legit. You can use that. What about if you have a question that asks about density? Look at my next example problem. It says, what is the density of uranium hexafluoride at a certain pressure and temperature? The density? The density?
What even is density?
What's even hexafluoride?
I'm still lost.
F6. No, this is like.
You make me smile. All right. So,
I just don't know why
can you take the ideal gas law and get density into it? I'm going to give you a couple minutes to wrestle with it. See if you can.
Wait.
Now, this is the kind of thing. Remember yesterday I was telling you, when I was in college, I had problems in which I didn't actually have a formula to solve for it, so I had to derive a formula. This is an example of that. Like if you have the ideal gas law, you're given PV equals nRT. And the question is, what's the density? You know, I don't just do what's density? I think about, okay, I know how to find density. Density is mass divided by volume, right? So, in case you didn't know, density is mass divided by volume.
Oh. Jeez.
So is there a way that you can manipulate the ideal gas law to have density in it?
There is, Mr. Mono.
Knowing that density is mass over volume. So I'm going to take you back to the previous slide up here.
Uh-oh.
Knowing that D equals M over V, get density into that ideal gas law.
I got you. It's because M
Can't wait to see what you have.
I can't wait to see what I have too. This would be a fun one. M equals dV in my board. Oh my god, alright, I think I just get so much. Shh. Oh wow.
Got it?
Do you cancel out the volume terms or not?
It doesn't cancel out, but it's replaced by the density.
Yo,
You can't get the volume to cancel.
Did you just, is that English? Uranium hexafluoride. What is that?
No, I filled it.
You think I know? Can you read it for me? Because I don't want to be. What's the more than asking uranium
Isn't that
hexafluoride?
CH4 or something? Or no, it's-
What is uranium hexafluoride? Oh, I'm a periodic table.
I just used the above.
Isn't it like F6 or something?
Oh, uranium monkey. Mass. I don't have a periodic table with me, so I'm too lazy. 352, 352, 352, 352.
Do you solve strictly for density?
No, just try to get density into the ideal gas law.
Oh, that's it?
Yeah.
Oh, oh, Mr. I think I did it.
Oh,
Well, Abhinav, did you get this?
See how density is mass over volume? So if we can take this formula, look at what I'm pointing at, take
Yes.
this and get the mass over the volume,
Yes.
then replace it with a D.
Yeah.
That's what we have to do.
That's my
Here's what we're doing, just so we can move along. I'm going to take this, divide both sides by V. So PV times molar mass equals mass times RT. Divide out the V. Why am I trying to do that? Well, I want M over V. So I've got M on one side, V on the other. So I'm going to get M over V. Now, the V is gone from the left side. So on the left side, it's just P times molar mass. And on the right side, MRT over V is the same thing as, because it's all multiplying and dividing on the right, it's the same thing as M over V times RT. Aren't those two the same thing? MRT over V is the same thing as M over V times RT. Now, why did I do that? It's because of this. I know that M over V is the same thing as density. So I can replace this M over V with density. P times molar mass equals density times RT. And this now would be useful for the next question.
I'm 3 steps ahead of you, Mom.
So we have 3 different expressions of the ideal gas law. All have their own place. Anytime you're dealing with the density of a gas, you're probably going to want to use this version of the ideal gas law. Okay, so with that, get an answer for the next slide here. What is the density of uranium hexafluoride? This is a crazy formula of a gas. It's a crazy compound. UF6 is uranium hexafluoride. A uranium compound? Do you remember learning in Chem 1 that the heavier particles get, the more they stick to each other because of something called London dispersion forces? Remember learning that?
I remember learning about dispersion forces a little bit.
Here, I was so optimistic.
Yeah, you were.
Anyway, this is an ultra heavy molecule, and yet it's still a gas. The particles don't stick. And the reason that they don't is because it is very nonpolar. It's got a very beautiful symmetry to the structure of the molecule. It's what we call an octahedral shape. It's a shape that you haven't learned yet. And yeah, it is so nonpolar that the particles just don't attract each other. And it's a gas. It's a very, very heavy gas. So what is the density of this heavy gas? Get an answer, and the number is not enough. Come up with a unit of the density. Give the answer with unit. I'll be quiet for a moment.
Wait, Mr. Man, you know the answer already?
Yeah.
Okay, what does it start with? Because I have an answer.
It's a 2-digit number starting with a 1.
Mr. Boy, I think
Got that?
I do.
Good. Nice.
I'm infinite. Let me show you my work. It's algebra, my brother. God, you have to.
I can give you a straight answer. Not once.
You have a question, or are you just stretching? Okay.
Oh.
Show me your work.
Shh. Cook. Dude, he literally gave us the formula. Just plug everything in there. Thank you.
What? He's recording.
Oh, shoot. Oh.
Yo, I got the answer.
Wait, is that for this? God. Do we use molar mass as kg for this as well?
No, it's only for that root mean square velocity
Yeah.
formula.
Only for that.
That's the only time you use kilograms.
2-digit answer starting with 1. I got it. I think. Yo, driving 273 plus. I think I got it. I don't know. Plus 60.
Give an answer though. I'm not an answer. Give a unit.
Yeah,
Give a
that's
unit.
what I'm thinking of.
Oh, yeah, the internet?
See, the internet. Imagine that calculating yourself. Can be.
Yeah, uranium is 238 plus 6 fluorines, which are 19. 352.
Alright, so. Yes, I got that. Yo, dab me up right now. Yo, Mr. I got it right now. Oh. Bro, just shut up, bro. Just let me have my moment. Just let me have my moment, bro. Just let me have my moment, bro. Come on, this guy. Why am I not being right? Shut up. Let me have my moment. Yo, bro, what are the units? I don't know what the units are. I'm pretty sure it's grams per.
Density is mass over.
I was writing my total answer. Oh, what about you? This guy's still writing the formula. Wait.
ML.
60C, so 273.
I'll give you a hint. It's 333.
No, you're supposed to cancel the units out and see what it leaves you.
333.
Using the deriving.
What's gonna put?
Wait,
Abhinav, you know
Mr.
this
Moore,
guy asked
Yeah.
you-
this is not gonna
Abhinav,
be
tell
on
me
the
how you
test.
deal with R. This guy just asked me what.
Oh, it'll be on the test for sure.
It's a number.
Like the
What is
deriving
this guy?
stuff? Like cancel.
Nah. By the time you get through all the exercises, you'll know what formulas to use.
What do you mean? What's P? Pressure at 745 torr. You like,
Thank you, bro.
what's wrong with this guy? It says it right
Or I have
there.
to sit behind Ubby.
You mind if I just cheat on it?
He's not even wrong though. He's not even wrong though.
I got to sit next to him and get a.
Mr. Brown, I'm gonna give you a four. I'm gonna predict what's gonna happen. I'm gonna get up in the middle of a test and just go cheat off Abhinav. I'm gonna take his paper and just cheat. 2 minutes left before the MCQ answer. I'm gonna take a photo of this thing. Bring out my phone. Take a photo.
On the
of
AP test too.
On the AP test too.
Yeah.
I'll just have to go to the bathroom, and then I'm just gonna go slowly go there, take my phone, and take a photo. Wow, that's an infinite plan right
He's not
there.
even joking. That's
That's literally the strategy. You're the answer. You're doing the exact same thing. How are you not
Bro,
getting the answer?
Ubby, okay.
Exactly. You're doing it wrong, bro. It's torr, so it's 64.2, not 8.31 or 62.4. It's torr. Look, 62.4 equals torr over mole. You're using the wrong R value.
Like that took me too.
So like a lot, you know. Like,
I saw
funny
it.
unlock.
SAT
Yeah.
like that.
Okay, my friends, if you can come up with the numerical answer, you should also come up with the unit.
Cancel the tour.
I find it really helpful, even when I was a student, and I maybe that means that I was a bigger nerd than you, which I would be proud of.
Thank you. I appreciate it.
I always tell my kids at home, like my own children, I tell them that I'm going to teach their future bosses. That's you. Because you are all so high-powered, you know, and they're just Oxford kids. They'll do whatever. They'll work at the supermarket or whatever. No, I'm just kidding. My kids are super bright. Anyway, I joke with my kids all the time. What I really find to be helpful, and I always have, is carry the unit with my numbers that I put in, and then see how the units work out. Now, I will tell you that in physics, it's really essential that you do this. I think that you're going to be, you'll have, you know how like I was showing you what a joule is, kilogram meter squared per second squared? You have to do that a lot and analyze units a lot in physics. It's good to get into that kind of habit now. The number is not that hard to come up with. You just calculate, crunch out the numbers. It's 12.6. But what's the unit? Grams per liter.
Yes,
yes.
Sir.
The torr cancels the torr in R. The Kelvin in the denominator cancels the Kelvin in R. The moles in the denominator of the numerator cancels the moles in the denominator of the denominator. And we're left with grams in the numerator, liters in the denominator. Nishika?
Oh, wow.
Maybe they're here for one of you and not me.
No, I think she was looking at you.
Oh, okay.
I think she wanted to hear you.
So yeah, 12.6 grams per liter. We all good with that?
Wait.
Okay, now I just have one last question. It's not even going to take us the last 10 minutes. I'm just peeking back there. Man, I'm a total failure. Look at what has happened.
It went the other way.
It went the other way. Somehow, even with the vapor pressure of ethanol, there's a lower pressure on the right than the left. That definitely was not supposed to happen. If they were equal, I'd say, oh, there's just some leak somewhere in the system. Now I don't know what to say. I'm just embarrassed now.
Oh, wow.
Give me like 5 cents.
Are you talking?
Okay.
To you.
Give me a nickel.
Oh, God.
Yeah, I feel like I should just stop teaching now,
Yes, please.
as my demonstration has made a fool out of me. All right, if I can have your attention for this last thing.
I mean, bro, it's so bright.
Oh, she back.
Hi. You want to go now, or you want to wait a few minutes till we're done here? This is your chance to be a star, William. You better take it. Thank you. Okay, now this is our last example problem. I'd like to just have you walk through this one. This, again, is not a big deal. It's not difficult. You did questions like this in Chem 1. What I want you to do, two things I want you to do. Number one, I want you to do a reasonableness test when you get an answer. Does this answer make sense based on what happened in the problem? Do that. And I want you to see, I've given you a hint as to how to do this problem. If you remember in Chem 1, you had lots of individual gas laws. You had Boyle's law, P1, V1 equals P2, V2. You had Charles' law, V1 over T1 equals V2 over T2. And so on, and then we went through a whole bunch. I'm going to tell you that in this class, I just want you to remember one gas law, the ideal gas law. And you can get every other PVT kind of gas law from that. And here's what I mean. It says, for this problem, we have a volume of a gas, a temperature of a gas, 30 degrees, and a pressure of the gas, 710 torr. But then the volume gets compressed to a new volume. So we have a V2, and it changes to a new temperature, 820. There's a T2. And the question is, what is the new pressure? What is, that's a bad P. What is the new pressure of this gas? This looks like a problem that you would have used the combined gas law for in Chem 1, if you remember what the combined gas law was. But I am going to suggest you take all these kinds of problems and just identify, it says put all constant terms on one side. So that means this. What is not changing? In pressure, volume, moles, R, and T, what is not changing in this problem? The moles of the neon are not changing. It says neon is stored in a cylinder. Nowhere in the problem does it say that more neon is added. Nowhere in the problem say that some of the neon is removed. It does. All the neon is contained in a sealed container here. So the N value has not changed. And the R value, of course, is the constant. That doesn't change. So keep the N and R on one side of the equation. And then put everything else, everything that's changing, on the other side of the equation. Pressure, volume over T. You do have to divide the T out. Don't just move it over. Don't say PVT. Divide out the T. So you'll have pressure, volume over temperature. Now, when the pressure, volume, and temperature change, they're still going to, the new P times V times T is still going to equal NR. So that means this. The new pressure, volume, and temperature are going to calculate to give the same thing that the first pressure, volume, and temperature gave.
This was the yes.
So the ideal gas law is all you need. And when you look at the equation sheet, it doesn't have those individual gas laws on it. It just gives you the ideal gas law. You figure out the rest of them from there. And you might just remember them from before, and that's fine. But if you don't, you can use this for all of them. Okay, now go ahead and crank out the answer to this. And again, the other thing I want to ask is the answer reasonable when you get it? Take a moment and do that. You don't need to. You don't ever use the N here. You'll just use this.
It's a constant value.
Yeah, just use the changing values. Great question, too. I meant to say that. Thank you for asking. We have a volume on the left and a volume on the right. And I know that we got this volume out of the ideal gas law. When you use R, you have to have your volume in liters. However, if you don't have R in the calculation, you can just leave the volume in milliliters. As long as you have milliliters on one side and milliliters on the other, that conversion will cancel out. It doesn't matter.
You said don't worry about moles and water.
Right. You don't need the N and R at all. You just need this. So it's just algebra. Put the numbers in and calculate your unknown.
Wow, what kind of number is this? I got this, my brother.
Yeah, sorry.
Oh wow, 2 for 2.
Is it reasonable?
Low key.
Is it a reasonable? And why?
Not really.
Why would it be a reasonable answer? It's a ridiculous answer, but is it reasonable?
It's kind of unreasonable.
It's not real. It's
It's not reasonable. So it's unreasonable. You're not trying to say?
Can we just check the... This is one of the homework problems.
Oh, how does he know? It's because he done all of them already, didn't he?
It's not
It's not reasonable.
You did like 51, 2, 2, 3, something.
Yeah.
That's the new pressure.
Low key.
What even is sig fixing?
2 sig weeks.
Oh yeah, everything is
Oh, and then I did 2 right here.
It's 2.
Yeah.
Where's the...
So it'll be 51,000.
I do that.
Yeah, you're close. 969.
I got this.
We're solving for this term, the new pressure. When the volume and temperature change, what is the new pressure? New pressure is like 52,000 torr.
Yes.
Can I have to have 2 sig figs because my 25 ml.
52,000. I got 51,000.
It's counted.
51,000.
It's not the same thing as 2%.
Bro, that's such a high.
51,000, 52,000, something like that.
Okay.
It's big. Our first pressure was 710 torr, less than atmospheric pressure. Then it went nuts to 52,000, 51,000. Why? Is it a reasonable answer? Does the answer make sense? It should, yeah. Now, both changing factors cause the pressure to go up. We see that the temperature went up. Now, keeping in mind Kelvin temperature really didn't go up by that much. It went from around 300 Kelvin to around 1,000 Kelvin, 1,100 Kelvin. That was 2 point something times higher. So when the temperature goes up by 2 point something times, the pressure goes up by 2 point something times. The big change was because of the volume. The volume went from 500 ml, got compressed all the way down to 25 ml. The volume was compressed by a factor of 20. That shoots the pressure up by a factor of 20. It was the pressure change that really caused this to go nuts.
The volume change. Ah.
Did I just say pressure
said
change?
pressure change.
Sorry, it was the pressure. I did it again. The volume change is what caused the pressure to go bigger. Sorry. All right, so do some of the exercises soon. Quiz is on Monday. That's not too long from now.
I thought it was the temperature change.
Temperature change caused the pressure to go up, but not by that much, because when you change that temperature to Kelvin, it's not that much of a change. It's like less than 3 times bigger. But the volume is 20 times smaller. That causes the pressure to go up by 20 times.
81%.